Hi again. So this is the second part of my talk where I will tell you about free bicyclics now, free bicyclic groups now. Okay, so again, let's start with some motivation. So I want to start with a hyperbolic 3 manifold, which is obtained as follows. You start with a surface of genus G at least 2, you cross it with an interval, and then you glue the top to the bottom by a pseudo-Nosov homeomorphism. So it's a famous theorem of Thurston that a mapping torus, the mapping torus of a surface by a surface homeomorphism is hyperbolic if and only if the homeomorphism is a pseudo-Nosov. The fundamental group of this 3 manifold is a semi-direct product. And there is a dual cohomology class or a map to Z where we send the fundamental group of the surface to 0 and the generator for the circle direction to 1. A very interesting or curious fact about these hyperbolic 3 manifolds is that they actually fiber in infinitely many ways. What that means is I can write this, like this manifold can also be written as, it could fiber over. Maybe there is a genus 3 surface in there, and then it fibers over that genus 3 surface. So Thurston's fibered cone is a way to organize all these fibrations. So I'm telling you there are infinitely many fibrations of that same 3 manifold, and how do I organize all that information is via this Thurston's fibered cone. So this is a cone in the first cohomology of the fundamental group of the 3 manifold. It's some cone containing the original cohomology class U0. And what happens is that any primitive integral U, any primitive integral cohomology class in this cone, so any primitive cohomology class in this cone has the property that if I look at this short exact sequence, the kernel of that short exact sequence is finitely generated. And in fact, that is the fundamental group of a fiber, which is a surface. And this Z induces a pseudo-Nosov homeomorphism of the corresponding surface fiber. So for every primitive integral point in this cone, I have a surface fiber and a corresponding pseudo-Nosov homeomorphism with respect to which the 3 manifold fibers. So just remember this, for every cohomology class, there is a associated pseudo-Nosov homeomorphism. So here is a question. If the pseudo-Nosov homeomorphism corresponding to U0 has the stretch factor symmetry in that the stretch factor is equal to the homological stretch factor, is the same true for U? Or in other words, if the foliation corresponding to this pseudo-Nosov is orientable, does that mean that the foliation corresponding to this pseudo-Nosov has to be orientable? And the answer is yes, by this theorem of Macmillan. He shows that if there is stretch factor symmetry for some primitive cohomology class in that cone, then there is stretch factor symmetry for all primitive cohomology classes in that cone. So not just U0, if you know the stretch factor symmetry for some cohomology class, then you know it for every cohomology class. And in fact, he puts this result about stretch factor symmetry in a bigger context. So let me state the theorem first, and then I'll say more about the terms involved in the theorem. So if I start with a pseudo-Nosov homeomorphism and its mapping torus, and I suppose that the stretch factors of phi are equal, then something called the Alexander polynomial of the 3 manifold group divides something called the Teichmuller polynomial associated to that fibered face or fibered cone. And for us, what's relevant is that this Alexander polynomial, that basically determines the homological stretch factors of all the points, all the integral points in that cone. And this Teichmuller polynomial determines the geometric stretch factor of all the integral points in the cone. So you have these unifying objects which compute these stretch factors, and not just that the stretch factors are equal, but you have these polynomials are also very strongly related to each other. And Anna Parlak showed, she computed the actual factor. So the Teichmuller polynomial is equal to the Alexander polynomial times a different polynomial, and she computed exactly what that is. Okay, so now let me tell you very briefly what these polynomials are. So the Alexander polynomial is a more, it's a very well-known polynomial which can be associated to actually any finitely presented group. So I let H be the homology of the group mod torsion. Then this Alexander polynomial is some polynomial in this group ring, ZH, which is actually a group invariant. And let's say it's just written like this. And for us, what's relevant is that for any fibered, for any primitive integral cohomology class in my fibered cone, I can look at a specialization of this Alexander polynomial to get a LoRa polynomial. So the specialization is basically I evaluate the homology classes with respect to the given cohomology class. So then these will be some numbers and I'll get a LoRa polynomial. And then I can look at the roots of this LoRa polynomial. And the highest root is exactly the homological stretch factor of the pseudo-Nosov homeomorphism corresponding to that cohomology class. So this Alexander polynomial gives me the homological stretch factor. Here, maybe you might have heard about Alexander polynomials in the context of knots. So like Alexander polynomial can be defined for a knot, and that's actually a knot invariant. Like, and for instance, the degree of the Alexander polynomial gives the knot genus. So it's a very well-studied polynomial, and in our context, this is what we are interested in. That it's like one object which gives me the homological stretch factor of every point in that whole cone. Then there's another polynomial in the same group ring. So this is in the same group ring. This is called the Teichmuller polynomial. And this, so there is a little f here. This is for the fibered phase we are considering. So the fibered phase can actually be, once I have this polynomial, I can actually determine the cone using this polynomial. This polynomial is symmetric. And again, the most important thing for us is that for any fibered cohomology or any primitive integral cohomology class in that big cone, if I look at the specialization, I get a LoRa polynomial. And the highest root of that LoRa polynomial turns out to be the stretch factor of the pseudo-Nosov homeomorphism corresponding to that cohomology class. So again, I have this polynomial, which gives me geometric stretch factor for every fibered cohomology class. So summarizing this result in the three-manifold case, we have the Teichmuller polynomial, which packages the topological data over that fibered cone. We have the Alexander polynomial, which packages the homological data over the fibered cone. And remember, a guiding question was, when does homological data determine the topological data? And the picture here is that when, if I'm starting with a mapping torus of a pseudo-Nosov homeomorphism, if that pseudo-Nosov homeomorphism has orientable foliation, transversely orientable foliation, then the Alexander polynomial divides the Teichmuller polynomial. So the homological data is determining the topological data when the foliation is orientable. So instead of just looking at stretch factors individually, now we are able to study the stretch factors of pseudo-Nosov homeomorphisms over that whole big cone using these polynomials. So now I want to do similar things for the free group case. So for free groups, we construct these free bicyclic groups, similar to these mapping tori. So what we do is we start with a graph of rank n, then we cross it with an interval, and then we glue it back to itself using so right now I want to consider these fully reducible automorphisms of the free group. And the fundamental group of that 2 complex is the free bicyclic group. And to this free bicyclic group, I can again associate a dual cohomology class where the free group maps to 0 and the T maps to 1. So for these free bicyclic groups also, there's this interesting phenomena of splitting. These free bicyclic groups split in infinitely many ways as generalized H&N extensions. So what do I mean by a generalized H&N extension? It's basically a presentation of this form. And this is like, yeah, this is how a presentation of a free bicyclic group also looks. But the difference here is that for a free bicyclic group, this phi is an automorphism. But when I'm writing these as generalized H&N extensions, these phis, this is just an endomorphism of the group B. It need not be an automorphism. That's where the generalized comes into picture. So these free bicyclic groups also have lots of ways of splitting. And like Thurston's fibered cone, there is a cone picture, which was defined by Dowdall, Karpovich, and Leininger. So they define this cone of sections, again, sitting in the first cohomology of the group, where all it's organizing all the splittings of this free bicyclic group. So basically, for any primitive integral cohomology class in that cone, I get some kind of generalized H&N splitting of my free bicyclic group. So now I have these generalized free bicyclic, for every U, I have this generalized H&N extension, and I have this endomorphism of, so it's a known fact that this BU is also a free group. So I have these endomorphisms of free groups, and in fact, it is possible to define. So I define stretch factors for automorphisms, but it is possible to define stretch factors for endomorphisms. So it is possible to define these geometric and homological stretch factors for endomorphisms. And in fact, what DKL show in their work is that these stretch factors, they only depend on the cohomology class. So given a cohomology class U, I first get the splitting. From that splitting, I have an endomorphism, and I can define its stretch factors. But it turns out these, even for a given U, these splittings are not always unique. So you can have different endomorphisms, but DKL show that these stretch factors will all be equal for a given U. So now I can talk about stretch factor and homological stretch factor of a given cohomology class, of a given primitive cohomology class in this cone of sections. And I should have said, again, for people who are familiar with some terminology, this cone C is a component of the BNS invariant of the free bicyclic group containing U naught. The upshot is that it's organizing all the splittings of gamma. And now I can talk about stretch factors of every primitive integral point in this cone. The original guy was an automorphism, but these other guys may or may not be. Okay, so before I tell you our results, let me say what is a Macmillan polynomial. So Macmillan polynomial would be analogous to Teichmüller polynomial. So it's a polynomial in this group ring ZH. And again, this Macmillan polynomial, it depends on some choices, like what kind of mapping torus you choose for your free group automorphism. But it determines the cone of sections. Like as before, the Teichmüller polynomial determines the fibered cone. And again, if I specialize, if I specialize this Macmillan polynomial, then I get a Laura polynomial and its top eigenvalue, top root gives me the stretch factor of the corresponding endomorphism for you. And I should say this was also defined by DKL, Tardal, Kapovich, Leininger. So we have the Macmillan polynomial for free bicyclic group, and the Alexander polynomial is always defined for any finitely presented group. So I also have the Alexander polynomial with the same property of determining homological stretch factors. So let's see what kind of results we obtain. So the question we are interested in is, first question is, if U0 has stretch factor symmetry, do these other points in the cone have stretch factor symmetry? Or if any point in this cone has stretch factor symmetry, does that mean every other point has stretch factor symmetry? So that's one question. And the other question is, because I have these polynomials which determine, which help me compute these stretch factors, can I say something about these polynomials? Does one polynomial divide the other polynomial, like in the surface case or the three manifold case? So our first result is that if you have a free bicyclic group of a fully reducible outer automorphism, and C is the cone of sections, then the set of all primitive integral conjugacy classes which have stretch factor symmetry. So remember, in the surface case, it was either the whole cone had stretch factor symmetry, because if one point had stretch factor symmetry, then every other point had stretch factor symmetry. So it was either the whole cone or nothing. And here we get three cases. It's either the entire cone, so either every point in the cone has this symmetry, or there's exactly one residue class mod 2. So here I mean, if U is U0 mod 2, where U0 is coming from the original automorphism. So there's exactly one residue class mod 2 which has the stretch factor symmetry, or nothing has stretch factor symmetry, or empty, or nothing has stretch factor symmetry. When do these cases arise? The entire cone has stretch factor symmetry when phi, my starting automorphism, is positively orientable, which means it has a orientable graph map. It has a positively orientable graph map representative. So when that happens, this is analogous to the foliation being orientable. Then the entire cone has stretch factor symmetry. So every integral point has the symmetry. When phi is negatively orientable, then we don't get the whole cone, but we get basically half the cone. So we get exactly one residue class mod 2. So if phi is negatively orientable, so then everything which is equal to U0 mod 2, all those classes will also be negatively orientable or will have the stretch factor symmetry. And when phi is not orientable, then nothing has stretch factor symmetry in this cone. So this is a result analogous to the surface case, where if the foliation is orientable, then the whole cone has stretch factor symmetry, otherwise it doesn't. Otherwise nothing has. And our second result is about relating the polynomials. So again, we start with this free bicyclic group. And then I have to just write here the mapping torus, because the Macmillan polynomial depends on which mapping torus we start with. But as before, we get that the Alexander polynomial divides the Macmillan polynomial. And recall, Alexander polynomial determines the homological stretch factor, and Macmillan polynomial determines the stretch factor. And we also compute explicitly the quotient by the Alexander polynomial. And this nice equality holds when phi is positively orientable. So that's the nicest case. When phi is negatively orientable, we have to apply some involution to the Macmillan polynomial to get this. But up to that involution, we still get that the Alexander polynomial divides the Macmillan polynomial. And in general, when phi is not orientable, we get this result mod 2. So mod 2, this equation still holds. So what we have done is we started with trying to understand stretch factors. When does homological data determine topological data for individual free group automorphisms of individual fully reducible automorphisms? But we got a really nice picture over these, like this whole cone determined by a particular cohomology class of free bicyclic group. So it's a very nice picture where relating these stretch factors over the whole cone. And I think I'll stop here. Thank you.